and today we'll be presenting our work titled A Survey of Data Augmentation Approaches for NLP. So this is a work with Google AI Research, Mila, and Dartmouth, and has been published at the ACL 2021 findings. So the motivation for this work is that we're seeing increased interest in data augmentation for NLP for multiple reasons. Some include the fact that large neural networks that require lots of training data are becoming more popular, and there's more work on new tasks and low resource domains that require more training data. This area is relatively underexplored for NLP compared to computer vision. And further, we found that there was no comprehensive and unifying survey of data augmentation for NLP literature. Hence, we thought this would be a perfect opportunity to sensitize the NLP community to this growing area of work by kind of giving a bird's eye view as well as motivating interest in this area. So our paper is structured as follows. We first give a background on data augmentation, specifically for NLP. We talk about some methodologically representative major data augmentation techniques, and then go into useful data augmentation techniques for certain NLP applications as well as tasks. And lastly, we kind of discuss the challenges and future directions in this area. So firstly, what is data augmentation? Data augmentation basically refers to methods of increasing training data diversity without directly collecting more data yourself, for example, through human annotation. A typical explanation is that the augmented data kind of acts as a regularizer to reduce overfitting when training models. So this has been very common and pervasive for computer vision, but has been more difficult for NLP, where the input space is discrete. So getting more into detail, this is challenging for NLP because, first of all, it is harder to maintain desired invariances, and these desired invariances themselves are less obvious. So when you think of computer vision, there's some common invariances like, illumination invariance, translation, rotation invariance, and so forth, but it's definitely less obvious for NLP. Further, these invariances are harder to encode either directly into the model or used as a lightweight module that you can kind of apply stochastically during training. For NLP, you typically generate the augmented data beforehand and store it offline and kind of load it in during training, which is a less efficient process. And these desired invariances for NLP can differ substantially across tasks, whereas there are common computer vision techniques like rotation, which are more commonplace and task agnostic. So, what makes a good data augmentation technique? Well, ideally, a good technique should be both easy to implement while improving performance, and there's usually a trade-off between these two aspects. Rule-based techniques, for example, are typically easier to implement and use, but result in lower performance gains, whereas model-based techniques may be more cumbersome and difficult to use, but result in higher performance gains. Further, a good technique should result in a balanced distribution of the augmented data that is neither too similar nor too different from the original, as the former may result in overfitting, and the latter will result in augmented data that is not representative of the given domain at all. So now I hand it off to Varun to talk about our first major class of data augmentation techniques, which are rule-based techniques.
Hi, thanks, Stephen. So yeah, rule-based techniques. So we call them so because they have no pre-processing or in neither in their pre-processing nor in the actual transformation function or any step for the data augmentation. They don't use a heavy model, or they don't have additional parameters to learn. They may still have hyperparameters. So on the whole, they are easy to compute and predetermine. So some examples are easy data augmentation, which I was talking of at the start. So that's just a suite of randomized techniques like shuffling tokens or synonym substitution from WordNet. UDA is also, so UDA was a technique which showed how to do data augmentation on unsupervised data through consistency training. But why we list it here is that the underlying data augmentation primitives it used, such as back translation in NLP or RAND augment and others in computer vision, these themselves are either themselves rule based or they are built up of rule based techniques. uh, Finally, I'll also talk a bit about dependency tree morphing, and this dependency tree morphing is kind of nice because it kind of tries to bring over vision invariants and primitives into NLP by trying to find close parallels, and you'll see how. So, what dependency tree morphing does is, of course, like in you don't have a 2D adjacency structure like in an image for a sentence. You do have the 1D, but you can take the dependency tree, and with respect to the dependency tree, now we can define things like rotation and cropping in the sense that you have closed parallels. The same way you do it for, like, say, red black trees or in algorithms. So, yeah, for example, you can see here that. Uh, basically the this is useful for languages in which there is a lot of case attached onto the word, so a lot of different orders of the words are valid, kind of. So when you rotate, or like you swap trees of the same dependency parent, or you delete children, it works effectively. And moving on, so far we saw examples where the data augmentation technique involved transforming one root example and converting it into a new task example for data augmentation. But what you can alternatively do is you can mix up two or more examples, or mix them up in different ways. And of course, one of the most prominent techniques here is itself called mix up, because what it does is it does like a linear mixture of both the input and the label using weights randomly drawn from a beta distribution. And there have been many extensions of these in vision and natural language, like cut mix. And in natural language, people have tried to do all sorts of things with mixing embeddings. uh, in model based techniques, are techniques which actually use models in their pre-processing or in their transformation function, and typically these are seek to seek and language models, but need not be always. Like in back translation, you have the source to target NMT model and the target to source NMT model. Another technique is contextual augmentation by Kobayashi et al., which I'll go through. And then there's semantic text exchange, which Stephen will walk you through. It's actually also a nice generalization of contextual augmentation. So what is done in contextual augmentation is, if there's like you pick up words in the input sentence, you kind of mask them out, and then using a language model, you kind of try to predict alternative words. And these words should be non-identical, so they can't be the same word or inflections or other variants of that word. And you also keep the label aside so that your label doesn't flip. This is what contextual augmentation does. But now Stephen will walk you through semantic text exchange, which is like a generalization.
Right, so this was a new task proposed in an EMNLP 2019 paper, which basically involves adjusting an entire piece of text, for example, a sentence, the semantics of it, to match the semantics of a replacement entity, which is a word or phrase that is inserted into the text. So the authors proposed this Smarty pipeline, which involves entity replacement, similarity masking, as well as text infilling to perform this. So, sorry, can you go back to the
Yeah,
previous
yeah.
slide? If you look at this example, you can see that the top left text is about the weather being sunny, and we kind of can insert the replacement entity, which is the word rainy in this case, and through the Smarty pipeline can adjust the entire piece of text to have semantics related to the word rainy, which you can see on the top right. So you can see things like wearing sunscreen have been replaced with bring an umbrella, and sweaty has been replaced with like wet, and so forth. So for data augmentation specifically, you can think of doing this in order to alter semantics of the entire text with respect to a particular topic to produce augmented versions of a piece of text which differ in terms of semantics. For example, you can kind of replace noun keywords or key phrases with other keywords and key phrases. So that has actually been investigated in a later work called Gen Aug, which we'll also be talking about further on. So next, we also looked at multiple data augmentation techniques for common NLP applications. This includes low resource languages, mitigating bias, like gender bias, racial bias, and so forth, fixing class imbalance, few-shot learning, as well as adversarial examples. So one specific work is called Cause.ml, which is multilingual code switching data augmentation. So this has been used to generate augmented data for low resource languages, particularly by generating multilingual code switching data in order to better fine-tune multilingual BERT. What they do is they encourage the alignment of representations from source and multiple target languages at once. And they do this by mixing their context information. So you can see an example of how this works on the figure on the left of the slide. And they show improved performance across 5 tasks with 19 languages, which was quite impressive. Our paper also looked at data augmentation for many common NLP tasks, including question answering, grammatical error correction, neural machine translation, dialogue, as well as multimodal tasks. And and on this slide, you can see one of the tables from our survey paper, which kind of compares a selection of various data augmentation methods relating several aspects such as their applicability, dependencies, as well as requirements. So we definitely encourage you to check out this table in our paper. So one specific task this could be used for data augmentation is for text generation. This is because large pre-trained generation models like GPT-2 has the possibility to perform language generation in many domains and settings, including low resource domains. However, these models like GPT-2 still need to be fine-tuned to the specific domain. Otherwise, it can't pick up domain-specific features such as jargon or domain-specific vocabulary, length characteristics, as well as stylistic variables such as formality and sentiment. Apart from particular tasks like machine translation, however, most augmentation methods in NLP have focused more on classification, and there has been a kind of a lack of investigation on data augmentation for generation. So one work which investigates this is called GenAug, Data Augmentation for Fine-Tuning Text Generators, presented at the Deep Learning Inside and Out workshop at EMLP 2020. So the authors investigate a suite of different perturbation operations in order to generate augmented examples, particularly for fine-tuning text generators such as GPT-2. This includes synthetic noise, which is character level perturbation, synonym, which involves replacing words, hypernym and hyponym replacement, which kind of modify word granularity, as well as semantic text exchange, which I discussed earlier, which modifies topic level semantics. And you can see examples of augmented examples generated using these techniques on the right. So this has been motivated by intuition with a greater focus on modestly meaning altering perturbations toggling specific aspects of the text. And the authors showed that synthetic noise as well as hypernym replacement was able to improve performance, and that 3 times the original amount of training data seemed to be around the optimal amount of augmentation. Another work which kind of used the compositionality of meaning for data augmentation, which was presented by Jacob Andreas at ACL 2020, in order to construct synthetic examples for downstream tasks such as semantic parsing. Specifically, fragments of original examples of text are replaced with fragments from other examples in similar contexts, which showed improvement for these tasks such as semantic parsing. And now I'll hand it off to Varun to discuss some challenges and future directions.
So, towards the end of our paper, what we did was firstly to recapitulate what we have been getting at throughout the paper, and also to present like kind of a call for action for the future at what would be good to target for NLP research. So, we tried to outline challenges and future directions. So some of these would be obvious from the titles themselves. We'll be digging deeper into two of these, which might be a bit befuddling. So yeah, so in particular, we'll talk. Yeah, I'll just pause a bit so that you can read through some of these. But I'll be describing in detail, especially empirical versus theoretical and the span-based tasks. So, what do we mean by empirical versus theoretical? It sounds seems a bit puzzling, but initially, but what we mean is that if you take the typical timeline or presentation of a data augmentation method, it starts off with a task-specific intuition, and then it's formalized as a method in the paper. It works better empirically, and that is indeed shown well and robustly usually. But at that after that, it's the end of the story. So there is little or limited discussion on how it fits into the larger theoretical narrative. Like, why did this data augmentation technique work? What were the factors underlying its success, and what are even the factors to look at? What's the space of factors to look at? Is there a common way of coming up with these for any tasks? And how do the different variants or ablations of this DA method differ along these factors? And how do these hyperparameters line up along the factors of success? So yeah, that's what where we felt there was a dissonance between empirical novelties and theoretical narrative. Span-based tasks. So why are we talking here about span-based tasks? So these are tasks where the output labels correspond labels a label the labels kind of label multiple tokens or points in the input text, or more formally you can call them spans. Additionally, inputs themselves can be quite complex, but leaving that aside because they're documents. So what why this presents a difficulty is that there's no singular label at the global input level. So if you take tasks such as NER, which have one label at each token, or even something like event arc detection, which for a trigger will have like a tuple of many spans as the arguments. So why are they a challenge for data augmentation? Because you can't rely on just the input level variances. So what that means is most of your input level invariances, which are leveraged both by randomized or paraphrasing methods, like say token shuffling. Once you do token shuffling, your span correspondences can go potentially out of the window. Similarly with back translation, because the new tokens or spans that arise, you don't know how they map back to the original examples tokens or spans. Uh, so yeah, so these are some good data augmentation. Uh, so, so now, yeah, sorry. So now Stephen will talk about some good data augmentation practices we list out.
Right. So our survey kind of encourages these practices in order to improve the transparency, interpretability, and accessibility of data augmentation to the NLP and machine learning communities. In particular, we're encouraging unified benchmark tasks, data sets, and frameworks and libraries. So this is good because there's been some more investigation on this. For example, Augly recently by Facebook Research kind of has over 100 augmentation that supports four modalities. So it's good that there's more work on this. Things like more standardized evaluation procedures to better compare data augmentation techniques, as well as transparency. For example, transparent hyperparameter analysis and explicitly stating the failure cases of proposed techniques so people know what to further investigate to improve them. And lastly, of course, the discussion of the intuition and theory behind these techniques, which Varun kind of talked about. So one thing we encourage you guys to check out is our data augmentation for NLP GitHub repository. So this is where we'll keep constantly updated with the newest data augmentation work for NLP. New methods can basically request inclusion on our repository through a very easy pull request. And we'll also be updating our archive version of the paper in tandem with changes to this repository. So again, we highly encourage you guys to check this out. And now Varun will be talking about NL-Augmenter.
Yeah, right. So NL-Augmenter is this effort. It's happening as a part under the umbrella of GEM, which also happened at ACL. And basically, NL-Augmenter is an effort led by Kaustubh Dole. It's his brainchild. I and Steven are also part of this effort. And we thank him for allowing us to incorporate some of his slide content into the ensuing part of the presentation. So what NL-Augmenter addresses specifically in terms of data augmentation, the things Steven spoke about, especially from that it works on these 3 points which we have marked out, like unifying benchmark tasks and vocabularies, and especially making code and augmentations available, and also supporting evaluation procedures using these augmentations. So specifically what NL-Augmenter does is it provides a repo, a participative repo, where the NL community can contribute, curate a large suite of transformations. So people can just push their code, it will get, the PRs will get approved and it will get incorporated into like a common structure. So what is a transformation? So a transformation is something that, a function that converts a valid task example for a certain task to a new and distinct valid task example, and this can be specific to the task, and it kind of generalizes the notion of a paraphrase. And how it does this is, it instead of just saying you have the input sentence, you can take whatever you want from the task, like the in any tuple of input and output components, and define your transformation over that. uh, so yeah, it generalizes the notion of paraphrase. It's task specific in its notion of invariance, And you can see how a new data augmentation strategy automatically falls out of the transformation. And we make this process participative to allow us to benefit from wisdom and scale of the crowd. So we have as diverse and big a set of what do you call it, like a set of transformations as possible. I mean, one example is like add a knot. I mean, this is a toy transformation, you can think of it. So if you have sentiment analysis with binary labels, input sentence X and labels Y. So what this not X does is it introduces a not after the B auxiliary. So this zombie flick was worth the ticket and this zombie flick was not worth the ticket. But after that, this is not a valid paraphrase, mind you. But if you define it as also negating the label, flipping the label, then together this transformation is a valid transformation for sentiment analysis. Other than what we explained so far was how this helped the cause of data augmentation, but NL-Augmenter as an effort also advances certain other causes, like it helps bring more attention to LR language and domains, because you can define certain transformations which test for these kind of test situations more. And it can also help perform in general robustness testing of models to target specific capabilities. And we invite everyone to so yeah, you can open a pull request on August 31st, which is tomorrow, but you only have to open the pull request. You can The completion cycle is longer. So if you have any idea for a data augmentation, and you can and the code facilitates easily incorporating this, so we have interfaces for different tasks, and you just have to follow a set format to create a set of test cases and run it, and do a pull request, and then two reviewers review it, and so on and so forth. So far we have 43 implementations and 80 under review, and it's growing. We list out some of the transformations that are already in. So we have homophones, also changing the format of the date, like 8th August 1981 to 8/8/81, and also substitution of discourse markers, leaving the meaning invariant, like later and subsequently. Also, increasing cultural diversity of names by substituting them, style transfer, and also decontextualize sentence reordering. So you can reorder the sentences, and then it does some fixes like co-reference and things like that to make it to make the new order sound sensible at the document level. Yeah. So you can see that it is like a whole zoo of such transformations already out there, and we hope this grows. And ultimately, the ambition can be whether we can learn that to craft new augmentations even automatically, but that's just an ambition. And yeah, we invite you to visit our repo and contribute. And this is the whole team behind the effort of NL Augmenter. We also encourage you to browse this related earlier paper. And now Stephen will talk about another effort both of us have been involved in.
Right, so very briefly, just to end off, we also have a controllable generation workshop taking place on December 15th at NeurIPS. Specifically, it aims to explore disentanglement, controllability, and manipulation for the generative vision and language modalities with an exciting line of speakers, a live QA and panel session, and so forth. So here you can see, some of our invited speakers and panelists. So we have a variety of people from Washington, Facebook, and so forth. We also have some important dates. So we're looking for papers as well as demo submissions, with paper submission deadline on September 27th and demo submission deadline on October 29th. And specifically, for our call for papers, we're looking at any type of work which kind of addresses controllable generation. This can look at new methodology and algorithms, as well as applications and ethical related issues, such as things related to the risks and dangers of deepfake and fake news for controllability. We also look at things such as different controllability tasks like semantic text exchange, style transfer, image synthesis, as well as cross-modal tasks such as image captioning, evaluation and benchmarks, cross-domain, for example, work in interpretability, disentanglement, representation learning, as well as position and survey papers, especially ones which kind of look at areas which have been neglected in controllable generation. We're also looking for any sort of demos, whether research related, demos of products, or interesting side projects. which are creative, well-presented, and attention-grabbing. So things like creative AI, style transfer, interactive chatbots, controllable image enhancement systems, and much, much more. So feel free to submit either papers or demos and to check out our workshop on December 13th. So this is an organizational effort, again, with me and Varun, as well as some others from Stanford, Microsoft, and so forth. Yeah, so thank you so much for listening to our presentation. And we hope our survey paper and presentation is useful for researchers and for motivating further work and interest in data augmentation for NLP. Please make sure to check out our paper, as well as, of course, our GitHub repository, which I stated will be continuously updated with the newest data augmentation work. And again, thanks to Varun, as well as our other co-authors, and of course, Walid and Aditya for inviting us to give this talk. Thank you.
Thank you, guys. That was a lot of work. Vikas has a question. Are you planning to join the discussion in the next half hour, or would you like to ask the question here?
Quick question. I won't be able to join it later. Just where can I see these slides?
I will be sharing them with the group.
Okay.
After the talk.
Thank you. That should do it. Thank you so much, Walid.
Of course. Okay, so Stephen and Varun, do you know how to join the